This section is, or this lecture will be 3.5, and I'll call it part 1. I'll probably just start breaking up the lectures into, 2 little parts. So this will cover implicit differentiation. So what is that? Some functions can be defined by expressing one variable explicitly in terms of another variable. What exactly does that mean? Some functions can be defined by expressing one variable explicitly in terms of another. One example is like if we had y equals x cubed minus say 5x squared plus 9. If you notice, we have y isolated on one side and all the x stuff on the other side, right? Pretty much what we've been doing up until this point, right? There's a good chance you haven't seen like a y squared or y cubed or whatever in the math courses that you've taken out, right? It's always been like y equals something with a bunch of x's. That's what we mean by a function being expressed by one variable explicitly in terms of another. So we have y, that one variable, expressed in terms of x. But how does that differ from the implicit differentiation? Well, some functions are defined implicitly by a relation between, right, b/t means between x and y. Now, an example of this one could be something like x to the fourth minus 3x y squared plus 6y equals 2. So let's look at the major differences, right? What's going on here? Well, we have x and y on the same side right here, but also something that makes it more complicated is that you now have multiple powers of y. We have like y squared, right? So big difference between uh, explicit functions and implicit ones. And you can derive both of them, right? Like we took, for this one right here, the first one, the derivative is straightforward, right? Like y prime is just equal to 3x squared minus 10x. How we find y prime in this case, right? How will we do that? I mean, maybe you're thinking, oh, we got to get y by itself or all these other little things, but it's hard to get y by itself. Why? Because you have a y here, a y squared here. They're all different powers of y. We can't factor out a GCF. So that's what implicit differentiation is all about. How do you derive implicitly? Well, the trick is to derive implicitly, you just have to remember basically one thing. It involves the chain rule. Okay, if I have d dx of, say, y, like we're just deriving y, well, remember, these are two different variables right here. So this y is not going to disappear. This is just going to become dy dx, like that. That's the generic form. Or you can say, or you could say it's just d dx of y equals y prime, right? That just means the derivative. And that's the gist of it right there. But what happens if you have multiple powers of y, right? Like, we're going to solve this one in a little bit. Like, you notice we have that y squared right there. How do we go out there and derive y squared? Really, y to any power other than 1. So remember, d dx of y is just y prime, or dy dx. What if I had d dx of, say, y cubed, like that? Well, you still have to apply the power rule like how we did with x's, correct? So like if we had x cubed and we were taking the derivative of x cubed, it would just be 3x squared. It's very similar right here, but since we're deriving with respect to x, we're still going to have 3y squared, but then we have to change the inside or take the derivative of y with respect to x. And in doing so, you have dy dx, like that. So the derivative, when you implicitly differentiate with respect to x of y cubed, is 3y squared dy dx. You will always have a dy dx piece that comes out when you implicitly derive with respect to x. That's always going to happen with the y component. It doesn't matter what the power of y is either. Okay, like if I had, let's say I had d dx of, say, 5y to the ninth power, like that. Guess what? You're still going to do power rule. So 9 times 5, that's going to give you 45. And then you're going to have y to the 8th. But then you have to change the inside or take the derivative of y with respect to x, which is dy dx. So that would be your derivative right there. So we'll come back to this one that I wrote right here, but we're going to build up to it. Okay? Let's say we want to find dy dx of x cubed minus 5y squared plus 2y equals 8. So how do you know whether or not you're just doing normal derivations or implicit differentiations? Well, the second you have x's and y's on the same side and different powers of y and multiple y's, you have to implicitly derive the thing. That's how you know. It just looks nastier than the normal expressions like y equals a bunch of x stuff that we normally be dealing with. So what are we going to do right here? We're going to take, again, the derivative dx of both sides. Okay? Remember, whatever you do the left side, you got to do the right side, right? Math's about keeping stuff equal. So every single piece, we will take the derivative with respect to y. So right here, what's the derivative of x cubed? That is just 3x squared. What's the derivative of 5y squared? Well, remember, whenever you have some y term, you're going to have a dy dx pop out of it, but this works very similar to this one, right? We're going to do the power rule. So we're going to have minus 10 and then y to the first, but then we're also going to have a dy dx. Now let's move on to the next piece, plus 2. What's the derivative of y? We saw that up here implicitly. It's dy dx. And all that is equal to, what's the derivative of a constant with respect to x? That is also just 0. So remember, we're trying to find dy dx, right? The derivative of this function. How do we do that right there? Well, we need to isolate dy dx, right? Because look, we have dy dx here, dy dx here. We got to get that thing by itself because we're trying to find dy dx, right? We're going to have to isolate dy dx. Like 99% of the time, whenever y'all implicitly derive something, you're gonna have to isolate dy dx, meaning we have to solve this equation now for dy dx. So how do we do that? We need to get all the dy dx stuff on one side and everything else that doesn't have a dy dx on the other side. So these two things or terms have dy dx. We're gonna leave it on the left side. Okay. You could bring it to the right side. It doesn't matter. Just get the dy dx stuff on one side and everything else without the dy dx on the other side. But I'm gonna go ahead and move this 3x squared. Why? Because it does not have a dy dx next to it. So we have this now. So we have negative 10y dy dx plus 2 dy dx equals negative 3x squared. Now, where do we go from this point? All right, because we're trying to get dy dx by itself. Well, now look at the left side. Since they both have a dy dx in common, that's the GCF, right? So we can actually take out a dy dx or factor out dy dx. If you factor out a dy dx from the left side, what's left over? Negative 10y plus 2 equals negative 3x squared. We're almost done. To isolate this dy dx, we move this chunk of stuff over. Well, how's this chunk of stuff connected to the dy dx? By multiplication. What's the opposite of multiplying? Dividing. All right. So dy dx is equal to negative 3x squared over, and I was going to say 2 minus 10y. I just changed the order of these, because the minus sign is a little better right here. But still, 2 still positive, and the negative 10 still negative right here. So this is your derivative. Yeah, it looks nasty. And yes, it has a combination of x and y. That's very typical when you implicitly derive. But that's basically how it works out. You're taking ddx of everything, and you're going to have to isolate dy dx. Sometimes they're both on the same side. Sometimes they're all over the place. But that's okay. You just shift it all to one side, like how we did right here. You move everything else that doesn't have a dy dx on the other side, and then you factor. You're always going to do this GCF step right here, and then you'll divide out what's left over the other side. Let's try sine of y minus x cubed equals 2y cubed plus 5x. So it's pretty nasty, right? You get the trig function, a y inside the trig function, a y cubed, all this stuff. But guess what? Same steps, okay? ddx of everything, both the left side and the right side. Everything gets the ddx treatment. So how do you do that with the trig function? Same thing, okay? You're still going to, the derivative of sine never changes, like that rule. Like, derivative of sine of whatever, it's still cosine of whatever times the derivative of whatever it is. So let's just start with that. What's the derivative of sine? It's cosine, correct? So we have cosine of y, but then you have to take the derivative of y with respect to x. That's the chain rule. What's the derivative of y with respect to x? That's the implicit differentiation part. That is dy dx. Moving along to the x cubed. What's the derivative of x cubed? That's just minus 3x squared. Now you may be wondering, why is there no dy dx after the x piece, but there is after the y piece? Because remember, we're taking the derivative with respect to x. If on the denominator of your derivative it's x, and what you're taking the derivative of has x components, you're not going to, basically if they match, you're not going to have that dy dx stuff floating around. Now let's go to the right side. So derivative of 2y cubed with respect to x. Well, we're going to have to do the power rule again. That's going to be 6y squared. But then we need to take the derivative of y with respect to x. So that's dy dx. And then derivative of 5x is just plain old 5. Now, if you notice, we have dy dx is on the left side and the right side, correct? So we need to get them on the same side. That's what we're ultimately looking for. It does not matter if you get them all on the left side or the right side. Okay, it really doesn't matter. I'm just going to put them on the left side. So to do that, we need to subtract this entire chunk over. So I'm going to subtract 6y squared dy dx from both sides. What does that look like? Well, now we have cosine of y dy dx minus 6y squared dy dx minus 3x squared equals 6y squared. The dy dx is on the same side, but remember we need to move everything else that doesn't have a dy dx to the other side. So we have to move this negative 3x squared over, and we'll do that by adding, right? What's that look like now? We now have cosine of y dy dx minus 6y squared dy dx equals 6y squared plus 3x squared. At this point, it's GCF time. You notice now you can factor out a dy dx from this. That's always going to happen, okay? You're on the right track. You know you're doing it right. If at the end, the second last step, you can pull out a dy dx from some side. Make sure everything has that dy dx, right? If you try to pull out a dy dx from this line right here, you cannot do it because this negative 3x squared does not have a dy dx multiplied into it. So if we factor out a dy dx, again, from these two pieces here, we're left with cosine of y minus 6y squared, and all that equals 6y squared plus 3x squared. And then lastly, we can divide, right? Divide both sides by this cosine of y minus 6y squared. We can divide both sides by it. So we get dy dx equals 6y squared plus 3x squared over cosine of y minus 6y squared. Now I bet some of y'all are thinking, oh yeah, we can cross out these 6y squareds, right? Right? Because we got one up top, one at the bottom. No, you cannot cross these out. Why? Because in order for you to divide out or cross out a 6y squared from this particular expression right here, every single term would have to have a factor of 6y squared. There's 4 terms here. 1, 2, 3, 4. Is 3x squared divisible by 6y squared? No. Is cosine y divisible by 6y squared? No. So this is your final answer. Don't get all slash happy and start crossing stuff out. You cannot do that right here. Remember, in order to reduce fractions, every single term within the fraction must have a common factor. Right here, only 2 out of the 4, right? These have a common factor. And you can't reduce by 3 either, right? Even though this is divisible by 3, this and this is divisible by 3, this is not divisible by 3. So you can't reduce the constants or the coefficients either. So that is your final answer. Let's give this one a go. X squared y cubed plus 3y squared equals 2x cubed plus 7. dy dx equals what right here? So again, how do we start? ddx of everything, right? Of the left side, the right side. Now, this one's a little more tricky, a little more complicated because now we're multiplying an x term times a y term. It's very similar to the example that I initially wrote. So how do we do that? If we're multiplying two different types of functions and we have to take the derivative, how do you do that? I got to use the product rule, right? So I'm going to say this is f and g. So product rule, make a note of that, right? You got to remember these things, right? The product rule and quotient rule, all that good stuff that's never going to disappear whenever you take derivatives, right? So remember, product rule says fg prime plus gf prime. Let's do it. So f times g prime. What's the derivative of y cubed? So that's going to be 3y squared, but then we have to change the inside. So dy dx. And then plus gf prime. Well, g is y cubed times the derivative of f prime. What's the derivative of x squared? That's just 2x. So that component's done. Now, you go on to the next piece, right? So remember, this is the product rule. F times g prime plus g times f prime. Plus, now we derive this piece right here. Derivative of 3y squared with respect to x is 6y, and then dy dx. What is all that equal to? Let's go to the right side. We have to take the derivative of the right side. This is just 2x cubed, so regular, plain old derivative. That's 6x squared. Derivative of 7, or any constant, is just 0, so that's gone. Where do we go from here now? Isolate, right? Got to isolate the dy dx's. So they are both on the left side. We just move this chunk of stuff over to the right side. Let's do that. I will subtract the y cubed times 2x on both sides. Remember, that's our ultimate goal, to get the derivative, dy dx equals something. What does that leave us with? We have an x squared, 3y squared, dy dx. Plus 6y, and then dy dx. And all that is equal to 6x squared minus 2x y cubed. So I changed the order right here, right? Because we put variables in alphabetical order. X comes before y. Still negative, correct? And the y is still cubed. So this is the same thing, right? We know we're on the right track. Why? Because the left side now has every single term, like this one term, it's all connected by multiplication. And this other term, they both have a dy dx in it. So what do we do? What have we done for the past few problems? We have factored out that dy dx. Now you may be asking, can we ever have like a dy dx squared? In these cases, as we're doing implicit differentiation, those would be second derivatives from implicitly deriving, but you're not going to be doing that in this course. That will come up in later courses. Okay. So right now, this is the I guess the worst of the implicit. You would just have dy dx. That's it. So if we factor out a dy dx, what do we have remaining? X squared, 3y squared, plus 6y, and that's equal to 6x squared minus 2xy cubed. And the last step is to divide by this component, because again, we're looking for dy dx. What I should do is I should put this 3 out in the front. This should be 3, let's say this is 3x squared. Yeah. We're going to divide both sides by 3x squared y squared plus 6y. So again, if you didn't catch that, I just moved this 3 out in the front right here. Okay, so same thing. I'm dividing both sides. So your derivative is 6x squared minus 2xy cubed. over 3x squared y squared plus 6y. Now you may be asking, can we reduce something right here? Can we reduce? Remember, everything must have something in common, at least one thing. There's four terms here. 1, 2, 3, 4. Are they all divisible by x? No, this one doesn't have an x. Are they all divisible by y? No, this one doesn't have a y. Are they all divisible by some number besides 1? No. I mean, it looks super close, right? Because you're like, oh, 6 and 6. 2 goes into 6, but 2 doesn't go into 3, right? Or like 3 doesn't go into 2. These don't work. So unfortunately, that is your final answer right there. Let's look at now x squared cosine of y minus y squared equals 4x squared plus 3. So derivative time, we do dx of everything. The left side, the right side. And as you can see, we're multiplying two different functions right here. We have the chain rule. Even if this was x squared cosine of x and you have to derive it, you still have to use the product rule. Sorry, I said chain rule 5 seconds ago. It's the product rule. Yeah. So product rule is still f and g, right? So f times g prime plus g times f prime. What is that? F times g prime. Well, that's going to be x squared because f times g prime. Well, what's the derivative of cosine? It is negative sine of y, but then we still have to change the inside. Derivative of y with respect to x is dy dx. And then we have plus g times f prime. Derivative of x squared is 2x. All right, so that was our product rule right there. Moving on to the y squared or minus y squared. If we derive minus y squared with respect to x, we get minus 2y to the first. Chain rule, we have to derive y now. That's dy dx equals, right side's very easy, right? It's x isn't just constants. Derivative of 4x squared is 8x to the first. Derivative of 3 is just 0. So that's it. You made it through the gauntlet. Now it's the same other steps like before, right? We have to gotta get the dy dx stuff on one side, all the other stuff on the other side. So we actually have a negative x squared sine of y and then dy dx, and then plus 2x cosine of y, and then we have minus 2y dy dx equals 8x. So we got to move this guy over, right? Because he doesn't have a dy dx. How do we do that? We subtract that entire chunk. Right? If it's plus 2x, it's minus, right, of that stuff. Okay, so that leaves us with a negative x squared sine of y dy dx minus 2y dy dx equals equals 8x minus 2x cosine of y. And where do we go from here? GCF, right? What do they both have on the left side that's in common? dy dx. That's all you'll ever pull out in these implicit cases. Even if they had a constant, let's say this is like a 10x squared and this is a 2y, don't pull out a 2, okay? Because you're not trying to isolate the numbers, you're trying to isolate the dy dx component, so only pull that out. Now we have negative x squared sine of y minus 2y equals the right-hand side. what do we do now? What we've done in the past, I don't know, 10 problems? Divided, right? Once we this step, we divided both sides about this component right here. So all this is equal to your dy dx. So with these problems, take your time, right? Because they're very tedious. And as you can see, you got to remember stuff like the power rule, the product rule, all that good stuff. It never disappears. It's not like, oh, we finished the section on product rule. That's never going to happen again. No, you will have to use the product rule forever. Like when you take engineering classes, for those of you who are going to study that, and embedded in those problems as you're deriving, the product rule is always going to pop up. But by then you have to be able to recognize that right there. Now, back to our favorite thing that we do in this course 50 million times, and that is find the equation of a tangent line at the given point. They always bring this up in Calc 1. It's like in Math 130, it was always find the domain of every little single thing. So our function right here is x squared minus xy minus y squared equals 1, and they want it at the point 2, 1. So we've done this type of problem, right? 50 million times already. What do you need? You need a slope and a point. They gave us the point. So we already got that. Oh, thank you. Thank you, problem. Easy. They gave us that. But the hard part is that we need the m, the slope. Where do you get the slope from? The derivative. How are we going to find the derivative right here? Got to take gdx at both sides, right? Why is this implicit differentiation not regular old explicit differentiation? Because you have xy, right? You also have a y squared. It's not just y equals something. Now, if we do this, right? Derivative of x squared, that is just 2x. Easy. What about the next piece, though? Well, x times y, multiplying two different functions right there. What does that mean? Product rule, right? Enter f. Ah, yeah. You got your f and g right there. And we have this minus sign, so I'm going to put minus first. And parentheses, because whatever we get out of there, we have to apply the negative or minus sign to it. So x times y, f times g prime, that's x. What's the derivative of y? With respect to x, it's just dy dx. And then plus g times f prime, well, derivative, g times f prime, g is just y. Derivative of f prime or x is just 1. So there we go. That's us deriving the x, y. Now we go on to the minus y squared. When we take the derivative of that, what do we get? Well, it's going to be 2y. We need to chain that y out. So the derivative of y with respect to x is dy dx. And then equals 0, right? Derivative constant is 0. So where should we go from here? Remember, we need to get dy dx by itself, right? That's the derivative. Derivative is just a fancy word for instantaneous rate of change, which is just slope. We need the slope, right? We're trying to find the equation of a tangent line at this point. So we need to isolate the dy dx, but first we need to get rid of these parentheses, right? How to do that? Gotta multiply that negative through. All right. Now, from here, what's the next step? Get everything without dy dx on the other side. So I'm going to subtract the 2x. I'm going to add the y. Now we have negative x dy dx equals, oops, not equals, minus 2y dy dx equals negative 2x plus y. And then from here, right, you take out this GCF of dy dx. That leaves us with a negative x minus 2y. That's equal to negative 2x plus y. And where do we go from here now? What do? We divide, right? We divide everything by this stuff that was left over. So now we can see, oh, dy dx dy dx is negative 2x plus y over negative x minus 2y. Remember, this is our derivative equation right here to that crazy curve that we were initially given. But we want the slope at one specific point, right? We want m at, and they said 2 comma 1. Remember, that's our x and y. So what are we going to do with that? We're going to plug in both of these values into here, right? Because now we have x's and y's to jam it into. Remember when we were explicitly differentiating and finding the equation of the tangent line, we only had to jam x in because there's always dy dx equals a bunch of x stuff. But with this implicit stuff, we have dy dx equals a bunch of x and y stuff. So we got to use both of these numbers right here. This is like your x and y. So we're going to have negative 2 we have negative 2 times 2 plus y is 1. Negative x, that is 2, minus 2 times y is 1. Then we carefully simplify, right? That's negative 4 plus 1 is negative 3. This is negative 2 minus 2 is negative 4. So we get 3/4. That is your m. Now, where do we go from here? Point slope formula, right? Because it wants the equation of a tangent line. We plug all this stuff in. So we have y minus 1 equals 3/4 x minus 2. So I'm going to come over here now. So we have y minus 1 equals 3/4 x minus 3/2, right? Because I'm just basically 3/4 times negative 2 is negative 6/4, which reduces to negative 3/2. And then we add 1. Now we get y equals 3/4 x minus a half, right? Negative 3/2 plus 1 is the same thing as negative 3/2 plus 2/2, which gives you negative 1/2. So that is your equation tangent to that line that runs through that specific point 2 comma 1. So it's the same thing that we've done before, right? When we were doing the explicit derivatives. It's just that now you need to incorporate both the x and y value into your derivative. Why? Because when we implicitly derived, we were left with x and y stuff that we have to substitute these values into. And then from there, it's still point stuff, right? But just take your time with it right there. So that concludes part 1 of 3.5. Okay. Check out 3.2. I'm sorry, part 2 of 3.5 to continue.